In this video, I'll be talking about the limits of sequence of sets. Before we get started on that, let's take a review on what we've learned from calculus. So in calculus, let's say we have a sequence of numbers, x1, x2, all the way to xn, and it might be infinite, right? Infinite number of numbers in that sequence, and then we defined the n tail of that sequence to be the sequence indexed from n all the way to the very end of the tail. And let's put that in a graph. So all of these points indicate the values of xi, and on the x-axis we have the index of n. So let's say this is x1, this is x2, x3, x4, all the way. And for any k-tail, we can find a suprema. So let's say we care about the 4 tail, which means we want the sequence starting from x4. And the suprema for that sequence will actually be this point, because it's the largest element for all the maximum within each cluster. And as we increase this index, the tail index, as you can see, the suprema actually gets smaller and smaller until it converges to 0, right? So we call that 0 at the end as the limit of the limit superior, which is the minimum suprema. And similarly, we also have a definition of infima, which is the minimum within the n tail. So as you can see, the minimum is also getting closer and closer to 0. So that's what we call a limit inferior. And in calculus, we have a very important theorem which states that sequence xn is converging if and only if the limit superior of xn is equal to the limit inferior of xn. So if we put an emphasis of the n tail concept, then this is equivalent of saying the limit superior of the nth tail is equals to the limit inferior of the nth tail. So now we have reviewed what we learned from calculus. Let's now make an analogy using the sets, using the sequence of sets. So we also need to define two important concepts here. One is a decreasing sequence of sets. The other one is an increasing sequence of sets. So a decreasing sequence of sets is basically a sequence that's Bn that is decreasing if Bk plus 1 is always part of Bk. So if we draw that in a Venn diagram, so B1 is the largest circle, and then we have a smaller circle B2, and then B3, and all the way. So if Bn is a decreasing sequence of sets as shown in the graph on the left, then the limit of these decreasing sequence of sets is actually the intersection of all sets. As you can imagine, the circle gets smaller and smaller until one point the set reaches its limits, right? So you always take intersection until the smallest set. So that's why we define the limit as the limit of Bn equal to the intersection of all Bn. And as n goes to infinity, this reaches its limits. And on the other hand, for the increasing sequence of sets, because We also have increasing sequence of sets, which is B1 is the smallest, and B2 is larger, B3 getting even larger, larger, and larger. Well, if we want to take the limits of increasing sequence of sets, we need to use the idea of union. So if we take the union of these sets, the limit will also be unique. Now we've defined the limits of increasing sequence of sets and decreasing sequence of sets. How do we generalize that definition to arbitrary sequence of sets? So here are the definition for arbitrary sequence of sets, the limits for arbitrary sequence of sets. Let's look at the lim superior first. Similar to our definition in calculus, here is the entail of the sets. We're taking the union of the entail. So if we increase n here, as n increases, the sets, the union of sets are actually getting smaller and smaller. This is because you're taking union of fewer sets, so the union of fewer sets will be smaller than the union of more sets. So in reality, this is actually, you can think of it as a decreasing sequence of sets. So let's just call it Bn, consistent with our previous notation. So this is actually taking the intersection of a decreasing sequence of sets. And then for the lim inferior here, similar idea. We are taking intersection of this entail, right? And then as n gets larger, the intersection of fewer sets is actually getting bigger. So this is actually an increasing sequence of sets. We also call it Bn. So you're taking the union of increasing sequence of sets. If we compare this definition for arbitrary sequence of sets to the definition of limit for decreasing increasing sequence of sets, we can perfectly match them. So we match the lim superior to the limit of decreasing sequence of sets, and we match the limit inferior to the limit of increasing sequence of sets. Okay. So now let's continue with the flow in calculus, where we sort of establish the relationship between the lim superior and lim inferior. Let's do that here as well. So what does it mean that omega belongs to the lim superior set? Let's spell it out by defining the omega, defining the set that omega belongs to. So let's look at the definition here. This is our definition for lim superior. And the outer layer is actually an intersection layer, which means omega has to belong to any sets that are part of this intersection. And the sets that are part of this intersection is actually the entail of the sequence of sets. So anyway, we need to have omega that belongs to this intersection, which means for any n, you can find omega in that entail, right? And if we look at the second layer here, which is a union of sets. So for union of sets, omega belongs to a union of entail if omega belongs to one of these AK in the n tail, right? So here, as long as you can find one K that is greater than or equal to n, that contains omega, then that is okay. Then the union of those AK will contain omega. That contains omega, then that is okay. Then the union of those AK will contain omega. So just to reiterate, omega belongs to lim superior of an. So let's draw it out and see if this can help us better understand the meaning of lim superior. So I define an indicator function that when omega belongs to this AK, we give it a value of 1, and when omega is not belong to AK, we give it a value of 0. So basically for any n, there exists k greater or equal to n such that omega is belong to AK. This is the same as saying for any n tails, we need to have at least one AK contains omega in that tail, right? So let's say we decide to put our n here. Then it doesn't matter in front of this n tail whether you have omega belongs to any of these sets. So you can have 0, 1, 0, 1, or even 0, 0, 0, or 1, 1, 1. But for n tail, there has to be at least one set that contains omega. So this AK has to be 1, which indicates that omega is in that AK. And then for the rest, you will always find some 0. But no matter what n you choose, you will always find at least one AK that is 1, right? So as you increase your n, there's always a set that has value of 1. And then to put that in language, it's the same as saying for any n tail, we will have at least one AK contains omega in that tail. And because it's for any n tails, so if you look at all the n tails, then we can have infinite number of n tails, which means we can have infinite number of AK contain omega. So that's the second expression here. Okay, so let's do the same thing for limit inferior of an. Well, for limit inferior of an, I copied down the definition here. The outer layer here is actually a union, which means we only need omega belongs to one of the sets contained in this union, right? So we only need we don't need the any condition here. We only need there exist, right? What does there exist? So there exists right, so that's when we need to look at the second layer, which is the intersection. So for any n tail, there has to be the case that all the AK in that n tail, when k is greater or equal to n, contain omega. So omega will belong to AK for any k greater than or equal to n. However, this only needs to be true for one of those. There exists an n such that omega is belong to AK for any k greater than or equal to n, and then we call omega satisfy this condition as the limit inferior of an. So I put some notes down. So omega has to belong to every single set in the n tail if it belongs to the intersection of all AK, right? Let's formalize what we just wrote in words. So we claim that almost all the sets have omega, but some of the sets in the front don't have omega, right? So that's the same as saying all but a finite number of sets, all but a finite number of AK contain omega. And very straightforwardly, we will rewrite that as only a finite number of events AK do not contain omega, which happens in the front of the sets, not in the tail of the sets, right? Not in the tail of the sequence of the sets. All right. Okay, so remember in calculus, we said that the limit inferior and the limit superior, they're equal if and only if the sequence has a limit, right? So what about the relationship between the limit inferior of a sequence of sets and the limit superior of a sequence of sets? So here I claim that the limit inferior is actually a subset of limit superior. Let's see why. Let's first go the first direction. So if we find an omega that is in the limit inferior of the sets, let's see if it's also in the limit superior of the set. So here is, we first look at limit inferior, which is what we have right here. Omega is in all sets in a finite n-tail with n large enough, or omega is in infinite number of AK, right? And that is actually exactly the definition we have for limit superior above. So infinite number of AK contain omega. That is this equivalent of saying omega is in infinite number of AK, right? So this actually leads to limit superior of AN. So for any element that belongs to the limit inferior of the sequence of sets, also belong to the limit superior of the sequence of sets. Now let's look at the other direction. So suppose we have omega that belongs to the limit superior of the sets. Does it mean it also belongs to the limit inferior of the sets? Well, let's write it out. So when an element belongs to the limit superior of the sets, we had number of events of AK that are not happening, which is same of saying number of AK that do not contain omega. All we know for limit superior is that there are infinite number of AK that contain omega. In terms of the number of AK that do not contain omega, there are two possibilities. One is that there are infinite number of AK that do not contain omega. The other one is that there are finite number of AK that do not contain omega. Well, for this case, when you have finite number of AK that do not contain omega, this is the exact same way of stating what is the limit inferior, right? All but a finite number of AK contain omega. So finite number of AK do not contain omega. So this part is indeed our lim inferior. What about the infinite side? When you have infinite number of AK that do not contain omega, does that satisfy what a lim inferior is? The answer is no, because if you look at the graph we've drawn above, there has to be only finite of sets that do not contain omega in order for the n-tail, all the events in n-tail contain omega, right? So if you have infinite number of events that do not contain omega, then we cannot have the tail of all the events that contain omega. So So this part does not, this part contains omega in the limb superior, but not in limb inferior. So omega are in limb superior indeed, because that's how we divide the limb superior set. However, these elements are not in limb inferior. So if I draw the diagram, the Venn diagram, this is what we have. And the inner circle is limb inferior sets, and then the outer circle is limb superior sets.